السلام عليكم ورحمة الله وبركاته. سامعين صوتي؟ Can you hear my voice? You see my screen?
وعليكم
Yes,
السلام.
Doctor. وعليكم السلام.
Okay. عليكم السلام. Okay. We will continue our lecture. We were talking about design and analysis, and we differentiate between analysis and design. We said we make sure of everything in analysis, and then we start to make our design. After analysis, we start making our design. I told you about the design hierarchy, which is very important if you want to design a complex circuit. You have a complex circuit, you have to divide the circuit into smaller sub-circuits and then work on that smaller sub-circuits. And we get an approach over this actually. And here we design an error check circuit, the same concept, with the same concept. We design an error check, which is a circuit to make sure of the data is transferred between the sender and the receiver without errors. We will design the circuit using the same concept, which is design hierarchy. First, we should return back to XOR and understand how XOR is defined. We have XOR and also we have XNOR. The XOR is just X or X or Y. One of the variables is different, means 1, and the variables are equivalent. This is 0. Here, this is XNOR, which is represented by XY or X dash Y dash. There is some kind of identities in the XOR circuit. These identities are specific to XOR. For example, XOR 0 means X. X XOR 0 means X. This means that if we XOR by 0, the output will depend entirely on X, because if we have 1 XOR 0, this means 1. If we have 0 XOR 0, this means 0. What about X XOR 1? This is going to give us X dash. Why? Because if this X is 0, this means the output is 1, because they are different. If this X is 1, the output will be 0 because they are equivalent. So X will be converted to X dash. X XOR X means they are equivalent. The output will be 0 in all cases. X XOR X dash means 1, because we are sure that they are not equivalent, because we are XORing two different variables. One is 1, the other is 0. The first is 0, the other is 1, and so on. X XOR Y dash is equivalent to X dash or Y. It's equivalent to X XOR Y all dashed. So we know that XOR is cumulative and or commutative. Commutative means we can change the position of the variables. We have the same logic. And associative means we can distribute the brackets. We can change the position of the brackets. The functionality of XOR is important, because we will say that XOR will implement the circuit, which is error check circuit. We want to implement the error check circuit, and the error check circuit depend entirely on understanding the XOR and XNOR logic and these identities. Now we move to more specific functionality or Boolean expression to understand more about XOR. XOR for 3 variables means if you draw them by Karnoff map. If you draw them by Karnoff map, you have a Karnoff map here. Okay, this is not okay. This is not Karnoff map actually. Either 4 or 2, you can say this is going to be like that. If you remember how to Karnoff map, how to number the Karnoff map, we say, okay, this is 1, this is 2, this is 3, this is 4, this is 5, this is not no 9, this is 4, 5, oh, no, 6, 7, and 8. Now we have A XOR B XOR C. If we have A XOR B, this is equivalent to A B dash or B dash B, sorry, A dash B, ANDed with C dash, and then we distribute this C one time is complemented and the other time is not complemented, and then we distribute the C complement to A B dash A dash B. We get these two expressions and distribute C to these two variable. We get C or ABC and A dash B dash C, A dash B dash C. If we look at these ones in the Karnoff map, they are located at 1, 2, 4, 7. 1, 2, 4, 7.
Doctor, shouldn't we start with the number 0 in the Kernoff map?
Okay, yes, you are right. You are right. That's why I'm confused. I said there is a problem here. Thank you for mentioning that. Frial, your name
No,
is
it's
Frial?
Hanin. Hanin.
Haneen, thank you, Haneen. Thank you. You are right. You are concentrating more than me. So that's good. So we have here, I'm saying, okay, there is some kind of a problem. So 0, 1, 2, 3. There is no 8, it's 7. So this is 4, 5, 6, 7. 1, 2, 4, 7. 1, 2, 4, 7. This. Okay, I draw another one. Okay. 1, which is here. 2, which is here. 4, which is here. 7, which is here. Okay, that's good. Thank you. Thank you, Hanin. Really, I was confused because the ones were near each other. Because this is XOR should be like that. There is no one adjacent to another one. No one adjacent to another. This is the nature of XOR logic in the Karnoff map. Even for the Karnoff map with 4 bits, you will find it like that. You will find it like that. One, 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 one. Here is one. Here is one. Like that. There is no variable. This is XOR between 4 variables. This is XOR between 3 variables. And XOR between 2 variables, you know it. I think you remember it, right? You'll find one here and one here. Or the opposite. This is 0, 0, 0, 0 is 1, right? No, this is 0. So it is the opposite. It is like that. Okay. So this is 2 variables XOR, 3 variable XOR, 4 variable XOR. This means the variables are not existing. The ones here in the Karnoff map, they are not existing beside each other because they are different. It's like Um, it's like what? It's like they are XORed means they are different, completely different. They don't have a common variable. That's it. Uh, but there is another very interesting characteristic of the XOR, which is what? If I count the number of ones, I will find them odd number. So we go to we can say XOR is odd function. This means if the number of ones are odd, this means the output is one. If the number of ones are even, the output will be zero. There are some kind of error detecting codes depending on the parity. We have two types of parity. We have odd parity and even parity. In the even parity, if we have an example like this is having three ones, this is odd, so we have one. By the way, this is not correct. Should be odd parity. This is even parity. Should be like that, unless you have you see something different, but this is should be like that. So this is an odd parity, means if the number of ones are odd, so this is going to give us one. If the number of ones are even, so this will give us zero. About the even parity is the opposite. If the number of ones are even, we have three ones here, so this is, sorry, this is odd. If it is odd, this is going to give us zero. And if the number of ones is even, so this will give us one. So this is odd parity and even parity. Okay, let me explain it in more detail. Suppose that we are working on odd parity and I want to transfer data between the sender and receiver. The sender is here. This guy is a very smart guy, has long hands and long legs, and he want to transfer data to the receiver, which is that one with very graceful body, and the data is like that. The data is like the one here, which is 0, 1, 1, 1. And they are working with odd parity checker. They are working with what? Odd parity checker. Okay? And they are agreed on that. They are agreed on the odd parity. So this guy knows that this is going to use odd parity, and the receiver will be highlighted or informed that it is odd parity. The data arrived to the receiver. The sender sent the data and the data arrived to the receiver. What about if we have an error like that? This is error. This one is error. So we are working with odd parity and the receiver look at the data. It will find what? It find even. This means the data is not correct. This data is not correct because it should be an odd parity. I found it as even parity, so it is different. This means the data transferred is not correct. Another example, if this zero is converted to one, this means I will send one, 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 which is even number of ones, which is not accepted too because we are working with odd parity. Okay? You understand it now? So this is odd parity and even parity. And I want to implement a circuit to do the error checking. Okay. So it's simple. I can have three input. If I have three input like the one here, X y, z, as the example I have seen before. I check for parity, and this is odd parity. This is odd parity. So the number, if the number of ones are odd, so I put one. The number of ones here is one, so is one, 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 and the number of ones here is even. There are two ones, so this is zero. This is one one, so it is one. This is two ones, so this is zero. This is two ones, so is also zero. This is three ones. Three is odd number. This means it is one. So this is odd parity checker. Odd parity checker. Okay, how to implement this? The circuit is easy because it is going to be depending on XOR. As I told you, this is parity is going to be depending on XOR. You see, we have X dash, Y dash, Z, and X dash, Y, Z dash, and X, Y dash, Z dash, and finally X, Y, Z. We have the inputs here, and if we find that the output will be an XOR between three variables. The XOR between three variables. Okay. Okay, let me do it by Karnoff map. If you remember Karnoff map, we can do that by, as Hanin said, you have to count by the starting by zero, not by one. So we have here X, Y, Z, and here 0, and here 1, 0, 0, 1, 0, 1 here, and this is 1, 1, and this is 1, 0. Okay, let me check. This is 0, 0, 1, 0, 0, 1, which is 1, 0, 1, 0, 0, 1, 0, which is 1 here, and 1, 0, 0, which is 1, 0, 0, this one. And the last one is 1, 1, 1. 1, 1, 1, which is this one. This is an XOR. As I told you, there is no adjacent variables. There is no adjacent ones. This means doing like sine wave like that. This is XOR functionality. This is an XOR functionality. So the way to implement this is to just making an XOR between two variables, and the output is passing to another two variable XOR using Z again. This is how to implement the circuit of the parity bit. Suppose that I want to implement 9 input odd function. We implemented 3. We already implemented 3. We have this circuit now. We can have it because I know how to make it. I have 3 input and 1 output parity checker. This is 3 by 1. I want to use design hierarchy to be able to make 9 input odd function. If I want to make 9 input odd function, this means I will have 2 to the power 9 entries in my truth table. And this is not feasible. This is not correct. You have to use design hierarchy to be able to handle this. The best way is to have 3 by 3, 3 by 1, 3 by 1 odd function. We have 3 copies of them. If we have 3 copies of them, then I have 9 by 1. No, it's not by 9 by 3. 9 by 3 first. This is this part having 9 by 3 odd functions. Then I get another one to collect the output of the 3 gates, and then or the three circuits, and then I come up with the final decision about the comparison between those two variables, those variables. Now I have the functionality working right. I have 9 bits. You can say we have 9 bits, and if the number of ones in the 9 bits, the number of ones in the 9 bits are odd, the output will be one. If the nine, if the number of ones in the 9 bits is even, the output will be zero. Okay. So we have now implemented the functionality here, which is impossible to be working with the truth table using just a simple implementation with the circuits here, just 3 by 1, 3 by 1, 3 by 1, and another one, 3 by 1, to have a 9 by 1 functionality. And of course, you can convert the XOR functionality by just using the XOR we have here. You can have the exclusive or using NAND gates. If you have only NAND gate, you can use this way to have NAND gate. And the design hierarchy is simplified by this hierarchy. We have 9 input odd function. We convert it to 3 input by 3 input by 3 input, multiple 3 inputs. We don't need all of this. We only need 3 input odd function, three of them, 3 copies of them. Then each one can be converted to 2 XORs, and each XOR can be designed by multiple NAND gates. This is just a design hierarchy to tell you what kind of circuits you will have. At this level, you have NAND circuits. At this level, you have XOR circuits. At this level, you have 3 by 1 odd function. At this level, you have 9 by 1 odd function. Okay, that's the design hierarchy. Now you have the design. You can have it using XOR gates or NAND gates. And that's it for today's lecture. If you have any question. Any question?
يعطيك العافية دكتور.
No, no, doctor. Thank you.
Okay.